So, ready?
Yeah.
So, welcome everyone to the Statler College Robotics Seminar series. For today, we have Dr. Rahul Mangharam from the University of Pennsylvania, director of the Safe Autonomous Systems Lab, and his interest is at the intersection of formal methods, machine learning, and controls, and he applies his work to safety-critical autonomous vehicles, urban air mobility, life-critical medical devices as well, and AI co-designers for complex systems. He is the Penn director for the Department of Transportation, DOE, $20 million, Safety 21, UTC. Yeah, he is the director of the AutoWare Center of Excellence for Autonomous Driving, which is a consortium of the 70+ companies and universities on open source EV software for open standards EV platforms. And he received the 2016 US Presidential Early Career Award Peace from President Obama for his work on life critical systems. He got the NSF Career Award, 2012 Intel Early Faculty Career Award, and he has won several ACM and IEEE Best Paper Awards on cyber physical systems, control, robotics, machine learning, and education. So please help me to welcome Dr. Mangharam.
Thank you.
Thank you. It's a great pleasure to be here. So today we're going to have a lot of fun. Okay, we're going to talk about some really exciting stuff and things that you can get involved in by the end of the talk, right? So I'm going to talk about how, we all are hearing this big rush and a lot of hype about AI, but when, so AI is good at things that we are not good at, like churning through a lot of data, but AI struggles with things that we are good at, like basically physical movements, physical manipulation, and navigating through the world. And so that's this kind of, ironic thing about AI, right? That it can do things that can complement us, but to really supplement us, it struggles a lot. So these AI agents in the physical world, and we'll look at it in a very fun context of autonomous racing and then beyond, right? So see. Maybe I'll try this. So my research focuses on life critical systems. So what does that mean? It means that when machine learning and AI are being used to make a life and death decision. So a lot of my work focuses on, say, like implantable medical devices where software is in a pacemaker or a defibrillator and it's pulsating your heart. And take that's a life critical problem, right? It's a big difference from, say, just using ChatGPT or something like that. But if you it just gives you something that is incorrect, well, no big deal. You can correct it over there. The other aspect is on, so in order to be able to design something, we can keep testing it. But if you do like 1 million tests, it doesn't mean that the system is safe, because maybe on the millionth and first test that you didn't do, that's where you find the problem. So you have to do what is called verification, where you exhaustively look at all possible variants of this. So say like you have a self-driving car, you want to make sure, well, does it work in night and day? Does it work on rainy days? Does it work in crowded and cluttered environments? Does it work in the environment where you have crazy drivers around you? But there are so many cases over there, we just can't exhaustively look at that. So what we do is we actually use a technique called formal methods, where we make these abstract mathematical and logical models of these systems, which we can then exhaustively analyze and search. And I'll explain some of that as we go through it. And we apply that to control systems. That means they are always interacting with the physical world, whether it's a device interacting with the heart, the vehicle interacting with the environment, or buildings interacting with the and the environment and so on. And under the hood, we use a lot of machine learning. So we are not applying machine learning, but we are using machine learning to model these systems because the dynamics are so hard. So you need to have some approach to actually capture these dynamics even while they are changing. And whatever research we do, whether it is in these areas of medical devices or autonomous systems or energy systems that we work on, we ask the same question, that how can we guarantee the safety and performance of these systems as they're working in a closed loop? And so obviously today we'll talk about autonomous systems only, and those are is a thing, right? So just as an introduction, I wear different hats. You might ask, okay, what does a professor do on a daily basis? So we keep wearing hats. That's it, right? So so I direct this X lab, and we call it X lab because we are always solving for X, right? So where X is actually the important life critical problem that we find. So we are not really a lab that says we have these tools like convex optimization or some kind of ML technique, and we use that to solve all the problems. We are the opposite. We say, okay, what's an interesting and hard problem? Let's go and learn that. And then we spend several years on that, and we build our techniques for that, and then solve that. Right? So some of my team is in the hospital with cardiologists, with neurosurgeons, even with dental physicians, and they are working with them. But you have to understand the cardiology problem. How do you model the heart? How do you understand the surgical procedure? Or with neurosurgeons in the veterinary hospital, where they are doing analysis on cats and dogs' brains when they have a tumor. How do you assist them? So you have to understand how those systems work, right? And so then, as Amar mentioned, I also serve as the Penn director for Safety 21, which is a Department of Transportation, National University Transportation Center. This is the largest transportation center that the DOT sponsors. And here our goal is to develop technologies for safe and efficient movement of people and goods. So it's a very broad mandate, but we are really looking at what technologies will enable the future of electric and autonomous systems, not just cars, right? I mean, cars is some fascination in the US, but I think we are looking at broader mobility and how your generation would actually approach mobility. You don't necessarily want to own a car. It's just too expensive, right? Insurance alone is so expensive. So, but how do you approach that, and how do we get to, but first on the technical side? I just stepped down now as of April 1st as a board member of AutoWare Foundation, but AutoWare Foundation is a non-profit a consortium of over 80 companies and universities that develop the world's leading autonomous vehicle stack that is open source. So this is not Waymo or Zoox or some big tech multi-billion-dollar company shoveling lots of money and having 5,000 engineers work on robotaxis. These are actually commercially viable vehicles running in Turkey, running in Estonia, running in robotaxis in Japan, buses in Michigan, and open source. So this is actually the power of open source, where it's a very complex problem and you bring in these experts from ARM and from Intel and from different software and sensor companies, and they all collaborate together. No patents, no proprietary software. It's all open source and it helps everyone. And I direct the AutoWare Center of Excellence, which is over 33 members now of different academic institutions. They all have vehicles based on AutoWare, and they do research in that. And we will soon have West Virginia University as part of that, right? So, and then there's F1/10th, which we'll talk about a little bit more later on, which is basically 1/10 scale autonomous racing vehicles. Fun because many of you all have taken the class here also, because you can learn to build, drive, and race these vehicles. You can learn the fundamentals of perception, planning, control. And so this is what we do on a daily basis. So normally when we talk about autonomous vehicles, we think about it in traffic, right? Say this vehicle here is trying to merge, and yellow truck is not giving them a hard time. But for you and me, okay, look, I can keep nudging and eventually we will get through. Not everyone is like a difficult driver like that. Not everyone is from Philadelphia. Many drivers are notoriously like, mean. But over for driving on the roads for an autonomous vehicle is to be safe, be as safe as possible. Safety is well defined, maximize safety. If I reach home 3 minutes late, 5 minutes late, I just blame it on traffic or the weather or something else. Nobody cares if I reach Morgantown 5 minutes late from Philadelphia because it's a long drive, lots of things can happen. And so performance is not well defined. It's like, yeah, come whenever you can, just kind of be on time, right? So we were like, look, we need a problem that is much better defined, and that's where there is some tension. We said, well, let's look at racing. So over here, I think we have Alonso and Vettel driving at over 200 miles per hour, going neck to neck, just inches apart, full throttle, and driving at the limits of their vehicle's handling over here. But they have to maximize safety, but at the same time, they can't be too conservative. You get penalized if you're too conservative, or you get penalized if you're too aggressive. If you're too aggressive, you crash, game over, you're out of the race. If you're too conservative, well, you won't be in the top 10. In fact, if you're just half a second too slow in your lap time, you're out of the top 10. That's the end of your career. And so here you have this tension, right? So, and our goal is how can you balance safety and restraint over there and aggressiveness and assertiveness? And how do you do that? I all do that, right? So it's not just about speed in racing, because it's in racing, actually, if you see the stats from 1950 to 2022, only 40% of the winners actually had the fastest lap time. The remaining approximately 60% were actually really good at achieving this balance of aggressiveness and restraint. And that's what we want to look at and we want to understand. So my obsession is vehicles per se. Vehicles are metaphorically and literally a vehicle for us to learn about them. But in the future, your future is going to be full of autonomous systems that are in the physical world. And you need to then learn how to actually understand how they can behave in and about human beings and be able to balance these kind of constraints over here, right? But what racing provides us is that you are operating at the limits of your handling. That means you really need to know what are the nonlinear dynamics of these systems. Like for your tire, if you push it, after some point, you will actually slip and your vehicle can flip or crash. So, but you have to get as close to that limit, because if you don't get close enough, they will outperform you, they will outcompete you. So we have high speed, high acceleration, very fast reaction times, and full nonlinear dynamics in this, right? So that just gives us a very clear-cut problem now. We have this tension of safety and performance, and we are operating with the full physics of that. We have to understand how to do that. So obviously, crashing is dangerous over here, and you don't want that to happen often. It happens sometimes because you are operating right at that limit, and then over here you also see that you might have lidars, cameras, radars, all these sensors, but the sensors only tell the pose of the other agents and maybe short term where they are heading to. What we really want to know is what's the intention of the other driver, and in machine learning we call it what's the policy. How are they going to behave under every situation? So we want to be able to extract that opponent's behavior or the policy of how they're going to behave, but our sensors alone are not going to give us that, right? So, and that's the goal of the first part, is to understand how can we estimate what the opponent is going to do next, and then how can we actually generate a strategy to outcompete them on the fly. We have never met this opponent before. We don't know anything about them. In fact, in racing, it's also strategies are secret. Every new season, there's a new vehicle. Conditions are different. The driver's mindset is different. You can't just go back to 1955 and start mining all the data every race is different. It's a small data regime. You can't use some supervised learning and sort of try to exploit that over here. Every race is so interactive, it's so dynamic. You're not repeating the same kind of motions like that, right? So how can we work with that also? So we'll talk about, so our overall goal with racing is that we can then achieve this sort of safety through agility. If I build a superhuman driver that's better than me, that's better than everyone in this room, then they can actually just allow us to drive. But when we are in a risky situation, and help us there. But just think of it more broadly, even in autonomous systems, where you want a system that has these kind of capabilities. So our first question over here is, how can we generate the most competitive agents that dynamically balance safety and assertiveness? And please feel free to ask questions, or or if you're not familiar with something or something not clear. And so here you can see these two racers. These actually were two F-110 vehicles in 2019's race. And this vehicle is using what is called a sampling-based planner and figuring out what are the paths it can take. But it sees the opponent over there and needs to crash with it. So don't take the red trajectories and figure out how that opponent is going to behave. So what we do is we model this problem. This is from a paper in ICML called Formula Zero. Formula One. And Formula One is a set of rules for the competition. But Formula Zero is just saying, it's like alpha zero, alpha goes zero. It's just saying, I know nothing about you, but I'm just going to observe you and very quickly I'll compete. That's it. That's our goal, but with full dynamics, continuous engagement like that, right? So what we're going to do with this problem over here is first we model this as a robust reinforcement learning problem, and I'll explain what that is. Essentially, you can think of it as, I have an estimate of a cost of a set of actions, states and actions over some time. I'm going to make some actions and I want to figure out, okay, how can I overtake you? And but I want to figure out how to minimize the cost. So that means, what is the path that is the fastest and will allow me to have the most progress? But the problem is that I don't know anything about the opponent. So we actually have to then model this as a mini max problem, where we want to minimize, the maximum cost that I would have. So I don't want to crash into you, and I want to overtake you. But this is a more general formulation. The problem is that I don't behave, and so I have this uncertainty regarding your behavior, right? So, and we want to parameterize that uncertainty by this set P over here for this state and action pairs. So that means I say, okay, this is my current state. What's the best possible actions I can take? And so since I don't know how the opponents work, what we will do first is that offline, we will generate a population of racers. They will keep competing, and what is called self-play. That means they keep having competitions with each other. And whoever wins goes to the next competition, and they keep competing. And through self-play, we basically then running millions of competitions with a set of good racers. That means they have good prototype policies, and they know how to race on different turns, how to overtake, and they actually can be very high performant. And so now we just have, say, like 20 policies like that, right? 20 good candidate racers. Where did they come from? They came from a competition, has nothing to do with the real racer out there that we're going to compete with. But then online, when we start competing in a real competition, we use what is called a belief space planning over here. Belief space is just saying that, okay, well, I'm observing you and you seem like out of these 20 agents that I have with 20 different policies, you seem like a mix of 6 and 13. And then I observe you more and say, no, you're a little bit more of a 19 kind of agent, but you're a mix of these candidate agents. I need to figure out what kind of personality you have or what kind of policy you have, but only based on these candidate policies that I've generated. So these vehicles over here, they have their sensing, perception, and their planners over here. Mostly we are trying to figure out, okay, how do we race around this track? And so when we do population synthesis, you can see these two ziggly arrows over here. they're basically competing. They're running through different races, different tracks, different opponent drivers. And whoever wins basically gets to migrate. It's called a hotter bath to a colder bath. So this is an approach called parallel tempering. So it's actually like a 1970s optimization approach of really coming up with. But we applied this in this sort of setting called self-play. So self-play is just saying we're not basing it on any known opponent, but we are just self-playing with each other. And then we generate these competitive agents through this replica exchange, Markov chain, Monte Carlo sampling. So that's the optimization technique of how this works. What is the outcome of that? The outcome is that I can get, say, maybe 20 prototype policies, and these are agents. That means they have the fast minimum lap times. The amazing part is that they also turn out to be very diverse. And we want diversity. We don't want all of them to follow the same race line, but then I can just figure that out, right? If you know your opponent, if you're playing chess against them or some competition, then you just, if they have some sort of tactic that they always keep using, that's not a good opponent then, right? I mean, that's an easy to beat opponent. So they have different race lines in isolated graphs if they're only racing on their own. And then they also have different ways of overtaking. They always don't overtake from the inside. They have diversity and they're very competitive, right? And that's what the elite and diverse. And that's what we want in our agents over here. Then apply them. Say this is our ego agent. That means that's my agent over here. That's the opponent. The ego agent uses what is called a sampling-based planner. That means it's sampling the space in front and figuring out what are dynamically feasible paths that it can follow. And then we need to estimate how is this opponent working and what are they going to do next with a high probability. And so say we want to figure out what is the path that they're going to take, not at just this turn, but the next turn and how they're going to actually navigate forward. So suppose I do know with high confidence what they're going to do here, then I can figure out of my sampled paths over here, what is the minimum cost path? And that's going back to that optimizing the mini-max problem. What's the minimum cost path to overtake that and outcompete that agent? Maybe I don't overtake them at the next turn, but I will eventually, right? So, or at least that's my goal. So we need to figure out how do I guess this opponent's path? I've never met them before, and I'm just observing them for the first time. So let's take an example where I just have 3 opponent models. So this is a little abstract. What is a policy? What is a model? You can just think of it as the behavior of how you are, for us, we don't necessarily explicitly think about what's our policy if you're playing a game, if you're playing tennis or ping pong, or then we are just sort of into in that sense. We're not machines. We are very much living and breathing, but we are also looking at the opponent. We're very interactive. The environment affects us, our fatigue affects us, all of that, right? But in this case, it's much more straightforward because all of those aspects are all coupled and bundled into how the opponent works. So let's say I have opponent model 1, 2, and 3, and this is called a belief space over here, right? So they are in how we observe the opponents. So say I have my ego vehicle is observing the opponent, and they are going to take, like say, they could take this path, this path, this path going forward with the opponent model 1, 2, 3 there. But they actually take some other path over here. So we actually say, okay, well, you are a weighted mix of these policies somewhere here, but we also have some uncertainty. That means you're not always following that exactly. And that's why we have this uncertainty ball. And that's basically saying that, well, that's the error in our estimate that we will have. And we want to minimize that uncertainty ball. And basically we're kind of tracking, kind of like Luke in Star Wars, he's tracking, and he just has one shot to make it there, right? So and then as you're following this opponent and observing them, you're tracking them and in this belief space. So this is like an abstract space of policies now, of how is the driver's intention, and you're tracking them and say, okay, well, of these 3 policies, it is mix of that, right? So so just play along that it is in this abstract space, and at some point you might study about this multi-arm bandit approaches. And so essentially what this is doing is this online adaptation. So it's just saying that I was never meant to like know exactly who you are, but I can figure out who you are. And then now I know what you're going to do next, and I can figure out what is a good way to overtake you if I have high confidence in how you are actually going to behave next. And I'm just going to lock in on you. Another way to think about it is like, say I have this pie chart of say 6 different opponent prototypes. Let's say in the big any one of them, it could be any mix. As I observe you, you start to get more weighted to some, and you're highly weighted, heavily weighted with opponent model prototype 5. You're quite similar to that opponent prototype. And then you're some other weighted mix of the remaining prototypes over there. And that's how we sort of can model the behavior, right? From some known prototype agents. So what we can see then is that, if I want to be safe, I want to keep a distance, and that's in terms of time to collision. I don't want to be in a very short time to collision with other vehicle. So I have what is called robustness over here, and it's just saying that I spend less and less time in this near collision zone. I'm keeping my distance. I'm becoming more conservative. But the more we see that the win rate falls from about 60% to 50%. So this is just a mini hypothesis, sort of validating that the more conservative or the safer you try to become, then you actually start to lose your competitiveness over there, right? Fine, that's that. But we don't want that. We actually want to have the cake and eat it too. We want to be safe as possible, but also be as competent. And that's where this online adaptation comes into play. And this actually kicks in over here that as I'm observing the opponent, initially I don't know much about them, so I'm very conservative, but I can actually still be at maximum safety, be at full aggressiveness, because I know very well how you are going to behave. I have studied you and have figured out how you're going to behave. And now I can actually drive very aggressively because I have very high confidence that you are this mix of these prototype agents. And so online adaptivity allows us to regain our win rate over here and be very aggressive but at the same time also have safety. That means we don't crash as often, but we are still winning at about 60% of the time in this case, right? So this is just showing you that these agents can actually learn and adapt in real time. Whatever theoretical work we do, we also put it in. This is all running just on these little platforms over here of the racing. So that car that did the overtake now, this is the ego agent, and then that's the ego agent behind. It's studying this agent. So in simulation, it takes about 150 to about 350 observations to actually lock in on the policy. And in actual real vehicles or these scaled vehicles, it takes about 400 to 600 observations at 10 hertz. So it's still pretty quick to figure out how the other agent is behaving. And the other agent is not like some deterministic agent. It is quite random in how it behaves. And we can still do overtaking very efficiently. So what if now, so do you have any questions with that so far? So one question would be that, well, what if your opponent is like none of your prototype agents? You came up with some prototype agents, but the opponent is maybe better or maybe just totally crazy for that, right? And you just couldn't model them. And so in machine learning, we say that is out of distribution. That means you have your data set and you have your distribution of your policies, but they're just something way out there, right? It's a new it's someone who is going to beat the current champion, the tennis champ, right? Sometimes you see like a lower seed just beating the top guys, right? They're just so much better. So then we said, okay, let's model this as a game theoretic sort of formulation. So I'll just give you the intuition. I don't want to get into the maths really. So the intuition really is that when we are doing this motion planning, it's in the continuous space, and it's a very like high, high dimensional sort of continuous planning. It's very hard to design a game theoretic formulation over there because the game is continuously evolving. The game is also very interactive. Like based on what you do, I do something else. Based on what I do, and it keeps evolving, and standard game theory usually models things in very discrete space, right? Like chess. Chess is discrete moves, go, or these or poker, all discrete games, right? So even the video games are in discrete space. Yeah. So over here, say you have your ego agent, which is in orange, and the green agent is the opponent. The ego agent starts off and saying that, I have imperfect information about my opponent. I know nothing about them, but I have perfect recall. That means as we drive till some checkpoint over there, and say that's maybe like 8 seconds in our case. It does not have to be 8 seconds, just arbitrary number. Observing you, and then I'm tracking what you're doing. And then I say, okay, I know everything, and I know every move you made, every nudge I did, every turn you took, or like that. And I know what you did so far. And now I'm going to map your behavior in a more abstract space, because in the motion planning space, it's very complex. There are too many variants over there. So what we do is we create this low dimensional space. I'm not telling you yet how we come up with it, but it's just on aggressiveness and restraint. And we map all these elite policies on a Pareto front. That means these are all like the best policies, and say, okay, opponents started here, they're somewhat restrained, and we are starting off more aggressive, and we become even more aggressive. This is more aggressive here. If I become more aggressive, then obviously, eventually I will win, but then I start to become. So I'm basically just saying, where are you in the policy space? And now how should I respond by just finding another policy? So here, this is more of a strategic thing. It's saying that if you have a policy that you have a fixed policy, it's a only but also a big assumption. How can I keep switching my policy to outcompete you? And that's what this is saying. Okay, where should you switch? So we are just again in this policy space, and the policy is really on how we're going to drive, right? Maybe I don't overtake you at this turn, but I will what we call game. That means we have a sequence of decision making, and eventually I will get very competent, and I will adapt to counter your policy. So what is the best counter strategy to your strategy? But I'm learning it on the fly, right? So as I mentioned, in this kind of motion planning space, it's the planning problem is continuous. And so it's very intractable to define a game over there, right? So the observation space, the control space, the action space, they're all very high dimensional and make the problem intractable. So we have to map this problem into a lower dimensional space, and that's policy space. Because when you're driving, you say you have this kind of sampling-based plan, or you're sampling ahead and saying, which trajectories can I take? I can't take the red ones because they're going to crash in the opponent, or they're going to crash on the track boundaries. So which is the best one? And I want to basically encourage high speeds. I want to have maximum deviation from my race line. I want to penalize, a high curvature and high velocity, and basically maintain a smooth trajectory like that, right? So I have all these sort of things that happen in the motion planning space, but that's what makes it a very complex problem. But I want to map it into the game. I don't want to just say, oh, how am I going to drive next? How am I going to drive next? I want to sort of think about it more. So what we do is we run essentially a lot of races, like I showed you before in this self-play, and we then map these agents as elite policies. So what combination of your motion planning parameters of how smooth and how you overtake, they're all mapped and then reduced into this very simple phase of aggressiveness and restraint, but they're all the best policy. That means they won the most races. And then after that, what we do is we run an approach called counterfactual regret minimization. And that's basically saying that if I know what you're going to do, what is the best thing that I should be doing? But it's counterfactual. I won't get into the details of that, but it's basically trying to figure out the best counter strategy I should have to outperform you, like that, right? So, or the opponent agent. So I'm observing this agent over here as we are driving neck to neck. And then at this decision point, I say, okay, so far I've got a snapshot. I'm going to switch policies now, and I'm going to switch till I can figure out how to overtake you and outcompete you, like that, right? the assumption here is that the other agent is not switching. If they're also switching and I'm also switching, then it just will get to 50-50. It is an even game like that, right? So I made it a little bit unfair that opponent is not as adaptive. So what we can show then is that, as the opponent is driving, we can actually outperform them, being game theoretic. We can have a significant increase in our win rate that goes to, again, from 56 to 59% for unseen agents and for unseen tracks. That means it generalizes very well, and being game theoretic is also very effective in this kind of continuous case. So our main goal here was to take this game theory and extend it from discrete to continuous spaces. And that's what made this very exciting. And I'll just show you some examples of that, right? So obviously, now this is more aggressive as we come to zero, and this is more restrained as we go up there. So if the opponent is here, I become more and more aggressive, eventually I win. Okay, fine, being more aggressive, you can win. But sometimes if the opponent starts off being very aggressive, and if I'm also very aggressive, we both will crash. So then I don't want that outcome to happen. But these are just observations from the system running. This is not something we just drew in PowerPoint, right? So actually what we saw was that our eco agent becomes less aggressive initially, and then when it finds an opportune moment, it becomes more aggressive and then it overtakes. But it's not always, basically being macho all the time doesn't help. Right? Figure out how to be agile and how to adapt. Because if we both crash, we both basically lose, right? Lose, we don't have a draw to lose. So this approach goes into like, what is the strategy to pick my next policy as I'm going through that, right? So I'll skip over the next few slides on how we do that in the math. So then, a lot of people who work in machine learning for robotics, they say, okay, look, we're using machine learning or AI, it's a black box, but we need it to be safe, especially if it's working in and around humans, then how can we guarantee safety? So one of the approaches that, control barrier functions. And I'll just give you the intuition, we don't have to worry about the math. Control barrier function is just saying that, okay, I'm going to drive through and I'm going to navigate through this classroom over here, but I'm going to always keep some distance. I'm going to be kind of some buffer room, right? So just think of a control barrier function as keeping a buffer so I don't crash into the walls or other agents. But the buffer over here is in the past, it was always preset. It was always saying, oh, be very conservative because they just wanted to maximize safety. But we are in the business of maximizing safety and performance. We have that tension. We can't just be too conservative. So we said, okay, well, how can we have adaptive safety with this control barrier functions? And so it's just saying that, okay, well, I don't always want to be very conservative. Sometimes I have to be this conservative, sometimes this, but how can I learn that, right? So we basically ran this now through an approach, and we showed that, look, if you're too conservative, in many games, you just lose, you just don't satisfy, how the agents can navigate and so on, right? So basically having a fixed operating point of being conservative or overly safe will not help you win. So what we came about was, I'll just skip to one of the slides over here, is that we ran these competitions, we observed how they behave and how we should in turn behave, and how much safety buffer we should have. So we basically encoded these observations in our machine learning model in this latent vector, and then we came up with a way to adapt how close I should be and what sort of constraints should I have and how I should adapt my safety constraint, and then that generates the candidate actions. So basically it'll tell you sometimes, oh, just slow down, just follow that car, find the right opportunity. Oh, here's the right window, now you can overtake. But it'll keep telling you what to do in each case, right? So I'll skip over the math. But so over here is that this thing scales really well for number of agents over here. So if I have more and more agents, then it still adapts really well. It really with agents that are increasing velocity and much more riskier agents that are just lower. And so you can see that here, it's trying to overtake, it follows, it doesn't overtake, then it follows, and it finds the right option moment. And then each one of them, it is actually adapting. I think it's just the loading time is causing it to not all play at the same time, but again, if you just follow, you can see how, and then with unseen planners, that means these other agents, we have never interacted with them before, and they behave very differently. So this shows that this is very adaptive, but we can adapt safety in this case, right? So it's keeping the same theme as we go on. And all these graphs that are showing over here is that, it's just saying that, look, our crash rate over here is below this threshold. That's like the purple, the magenta line over here. It's just saying that we are always maintaining safety. We're not guaranteed like to be safe all the time, right? But we are much safer than all the other approaches that we compare to, and winning much more often. Of course, many times you win because you just survive. All the other people crash, right? So, but over here, it's just saying that you're winning more often. And I'll skip over these graphs. And yeah, I think here's a better video. So it all plays together. So this is just again showing that it scales very well. And that's what we want to show with any kind of machine learning approach, that you trained on something, but it generalizes very well to other agents that are sort of different from. So the other techniques we use, mathematical techniques, I'm not going into the math, but I just want you to get the big idea here, is that we have this learning control barrier functions. How can I learn what kind of safety I should have with you and mathematically encode that in a machine learning model? Then conformal prediction is like a statistical approach to say, well, if your machine learning model is predicting something, how do you know that that is going to be safe or among the safe set? And so it's providing some kind of statistical guarantee that what it's predicting is actually within the distributions that it has been trained on. And then physics-informed machine learning is just saying that, yeah, you can train some reinforcement learning agent and it might work most of the time, but some erratically, like say your car it can only steer in this manner. Sometimes it will say steer 90 degrees, but you can't steer 90 degrees in your car. So because your car has some physics limitations in the structure and with the friction and with the environment. So you have to encode the physics in the machine learning model so it doesn't do stupid things or basically unfeasible things. It understands the laws of physics are encoded in that, and then it will conform to those laws. So it's not like just a RL agent that is really stupid and it could do something. It works most of the time, and that's what you see with off the shelf, that yeah, it works eventually after a lot of burning a lot of hours on some GPU clusters, but then sometimes it just doesn't work. And so we are really interested in that. Can we minimize that? Sometimes it doesn't work, but using these are mostly statistical approaches for ensuring safety. So another fun problem we worked on was called, well, you have these, the difference between me driving from Philadelphia to Morgantown, maybe I'll just do that once in a while. I'm not going to keep doing that every time. But in a race, you're going on these laps. But now every time you go on a lap, you learn about the terrain, you learn about how much your handles on turns, and you can keep pushing the vehicle further and further. And as you keep iterating through that, you can get faster and faster and figure out how close you can get to the limits. But so you want to build like an auto tuning system, say like but you have many different things you can tune, the mechanical aspect of the vehicle, the mass, length, width, the CG, the cornering stiffness, and then how the vehicle makes decisions, how the vehicle controls. And say if I tune it like this, I get some lap time of 25 seconds. I can do better over there. So then I figure out a different way to tune it, and I get 20 seconds, and it goes faster, and then a different way. And here, this vehicle you can see is drifting, on go any faster. It's come down to 15 seconds. But so how can we come up with an auto tuning system? But we want to do this optimization across mechanical control, and planning and decision making for the vehicle. So it's what we call as a multi-domain optimization. And that's why we did this paper at ICRA called super optimization. So tune a car is basically just auto-tuning your vehicle. And so that we want to have a reusable core autonomy stack. That means your perception, planning, control can automatically be tuned for this track and for that vehicle over there. And if you change the track and the vehicle, it'll just auto tune one and then for the next one. And obviously we want it to work in our small scale vehicles also, but because we want to get a little bit real. And so what we did was, again, I'll give you the intuition. We ran this through what is called a gradient-free optimization. And that just means that, look, the mechanical stuff, how it affects the planner, how it affects the controller, and how they affect each other, those relationships are very hard to determine just for that vehicle model. So you don't have like a gradient. You don't know exactly what those relationships are. So you use this kind of evolutionary algorithm approaches to then optimize. What was the result? We ran this through this optimization now, and it took all these parameters and figured out this is the best for this track, for this. We are overfitting for the track. And so, say normally you would drive, you would just take the dotted line and go into the apex of a turn over there, and then come out. You would brake, and then speed up. But in this case, what it does is that it actually comes in really hot. This is the zoom in over there. It comes in really hot and drifts along the turn and then zooms off again. So it actually is fully exploiting the vehicle dynamics and it's saying, okay, let's take it to the limit. And here what you see on the z-axis for the same track is the vehicle's wheel slip over here. It's a slip angle and just showing that the vehicle is really pushed to the limits. To push it even a little bit further, it will flip out. And so it's getting like a full drifting vehicle. And so again, whatever we do in simulation, we just put this, we trained this vehicle for this track in simulation, just put the vehicle down and boom, it just runs. And it follows the optimized race line, and then it is going as fast as we can along that track. Yeah, can you do better? Yeah, you can still do better, but this is a really good starting point for your vehicle to follow, to start with, right? So this is like automating the process of now adapting to different hardware and to different environment settings. So again, don't just think of it in racing context. We look at it more in a broader autonomous system. So I'll just spend the next 10 minutes of other projects very quickly. We look at how do you do localization. Like you have a robot that is in the world, you want to know where it is. And so normally you use approaches like particle filters where you're iteratively trying to figure out, what is the best match from what my lasers are seeing now, what my camera is seeing. But here we actually use a neural network, but we use a different kind of neural network. It's called an invertible neural network, which is essentially compressing the entire map into the neural network and then looking it up. And so localization is inherently an inverse problem. That means if you give the robot, if you know the robot's pose, I can just project the laser rays and then I can recreate the forward problem. And because there's only one solution for that. But in the real localization problem is this inverse problem here. Because here what we have to do is we're saying, well, I got some scan of the environment, but I could be in this corner, I could be in this corner, I could be in this corner, I could be anywhere because the scans are so similar. So I have what is called an ambiguous inverse problem, and I need to know where am I actually. And so this invertible neural network can, if we just train it in the forward path, then we can just use inference in the reverse path. And it uses a technique called normalizing flows, which is essentially mapping the distribution of poses to the distribution of LiDAR scans. And in LiDARs, and it not only works really well, because you can run this at 270 hertz on just a fraction of the onboard processor. And it can recreate maps. These are like city scale maps, and it can recreate them with less than 0.25 centimeter error. So very precise maps over here. And it also works really well with camera inputs, right? Just with images. So you can do localization. So the same structure is used instead of lasers. Now I just provide images and I can now run that, right? So you don't have to understand how it works. fully because there is a lot of math and theory behind how normalized, how invertible neural networks work. But essentially, we are trying to address this class of problem called inverse problems, which is all these very hard problems that we find in physics, in biology, in real life. And these neural networks can help solve those problems very efficiently. Localization is just one example of an inverse problem. And then it can run very efficiently for image-based localization on the Jetson, on these race cars at very high speed. And this over here is driving through the corridor outside our lab. None of these images are real, actually. These are images that are generated by the invertible neural network to say, okay, I know where I am. Let me generate what the map should look like. What should it look like? What should it look like? And so I'm just saying this is your XY position room look like, and I'm just saying, okay, this is how the room should look like. And it is generating those images. So just showing you that kind of this is the forward problem. And anyway, it localizes very well with very low XY error and very low angular error. So the nice part is it also exposes the uncertainty distribution, which means that you can use an EKF with these, unlike classic Monte Carlo approaches. Other projects we do are on like, okay, if you're racing on multi-friction surfaces, you're racing on non-planar surfaces, you're racing on off-road surfaces, how should you adapt your controllers so that, as you're going from different, if you're going from a very carpet-like surface to a very smooth surface and you're driving really fast and turning, how should you adapt to that? And you don't want to have like an error where you lose traction or you lose your control, and you want to have very low error as the terrain is changing, right? So we use different approaches over there. I'll skip over the details. And then we have a lot of projects on drones and collision avoidance and mission planning with formal methods so that these drones can operate in a distributed manner in and around cities also. So I'll just skip through. That's all drones crashing over there, but I'll skip through that. So one thing I wanted to go was, okay, well, how can you get involved? I'm going to skip through these problems just to maintain time. So let me just skip ahead. That's our lab over here. We have a lot of female engineers in our lab. Those are my kids also, and we have a lot of end of the semester celebrations with them. So as part, so I already spoke about one third of the research we do on autonomous systems. I'll just talk to you a little bit about some of the education and some of the outreach that we do with the real world, right? So beyond just working in the lab, and so I showed you some of these things with these F110 or what is now called Robo Racer. These are the same software runs on this small vehicle platform, runs on these mid-scale go-karts, runs on full-scale autonomous vehicles. The software just grows in complexity, but the structure of perception, planning, control, and these algorithms are changing, but it just has the same structure, the same APIs, and that's called AutoWare. And AutoWare, as I mentioned before, is the world's leading open source autonomous vehicle software stack. So with F110, we teach this course. Many of y'all have taken this course here. The main thing was, I was like, look, I know this stuff, but to build a real autonomous system, we need to know all of this stuff like that, right? Because if you join a company, they put you in like this subdivision, this department, this group subdivision, seeing out some system, or you're building like a subcomponent of a very large, system. So this is our chance while you're studying to actually work on a complex enough system, but that's not too complex also like that, right? So, and that's why we have this approach which brings all of these concepts that you study in many different classes together. And with this pretty simple vehicle, right? This is a off-the-shelf chassis, but now it has a GPU on board, LiDAR, camera. The main thing is not the platform. The main thing is all the algorithms that go into it and that you can then do for yourself. And that's the fun part. And so different simulators that we use with this, and there are actually newer simulators from what I have on this slide, and that allows you to basically design everything in simulation, and then you can move the code directly to the platform and then just adapt it for sim to real. And our goal is to help the community build, code, and race. And so you essentially go from concept to code to competition, and competition brings out like a different spirit and different part of your personality there. It's all friendly competition. So we don't just do simple like navigation. We are running SLAM, like simultaneous localization and planning on these platforms, right? We are not just doing simple navigation and following a wall or something. You're running modern navigation in path planning like RRT, rapidly exploring random trees, RRT star, and sampling based planners, and all of that. All of that runs natively on these platforms. You're not just doing PID control. You're running model predictive control over here, and you're basically doing optimal receding horizon control that is also very robust to the dynamic and optimized for the dynamics of your vehicle over here, right? So you learn all these concepts, you put them into action, and you push the limits. The nice part is that in the courses that we teach, and that are all free and open source, and everybody has there are no exams, there are no midterms, there are no tests. We just have race one after about 6 lectures, and that's basically following just doing reactive racing. Then we have race two, and then that is basically saying build a map and then figure out a path in that, and then you race much faster. And then race three involves all of these advanced, race line optimization and sampling based planners, model predictive control, reinforcement learning, all of that. And you don't have to do the whole thing. You can just do a subset that makes you dangerous enough. Right. So, and then students do a lot of different projects. In fact, just yesterday we kicked off all the projects, and then this is whatever their interests are, they spend a whole month on these projects over there, right? And so this is
Fucking your F-110 car ever felt like this.
Hello, it is I, Rich Shankar, and I am here to show how you can adopt our team strategy so you can also be fast like us.
Organize vite comme le fast,
Simple. You collect lots of data.
botão, maille le console canonely print so many lines.
You can use ROSBAG to collect data and use Foxglove Studio to visualize it. Let me show you.
so that's just an example of a race experience that students had. So these are many generations of students. So this guy, he helped start some of the work originally. He was the lead for motion planning in Tesla for 6 years, and then he left and he started this company like late last year called Bot Company. I worked with the CEO. The initial round was like 150 million in funding, but it's basically that the students become elite and they can follow their dreams. They can get jobs in places where they really want to go to, and many start up their own things also. The other course I teach is called Tiny Machine Learning. It's basically how can you do machine learning on less than $1 microcontroller, ESP32 chips, and then you use sensors, you use audio, you use images, all of that you can do. And this is also fully open source course called Tiny Machine Learning. Just Tiny Machine Learning at Penn. So students did they put cameras in beehives. They could the bees that could tell them where in the farm or where in the fields the bees actually were getting the nectar from. And these are just examples, of course. Of that.
Nice.
Just the last 2 minutes is so we have so with F110 there are over 90 universities worldwide that use the platform, and there are many competitions that we've had, over 24 competitions, and you can see all the students are really happy over there. They all have the same platform. The platform is not the big deal. It's a battle of algorithms. That's right. It's what you do. The platform is something that we just take the hassle out of, and then so last competitions worldwide in all these different countries, and they're all part of big conferences in robotics, transportation, control systems, and so it's a so this year the next so all of them, they have the track, they're building the race track map, they're figuring out the optimal racing line, they're coming up with their overtaking strategies, and then the competition will keep evolving to non-planar ramps and all of that as we go down. And so this is just an example of one we had in Detroit. You can see they're pretty agile as they go through this, right? So anyway, this is just some more how these. This was in Korea last year. You can see this is the final lap as they are driving through. Yeah, anyway, that's so that's just showing you, like, what's the. I just wanted to touch on one last thing. We have many workshops on the theory aspects. This is called MAD games, or multi-agent dynamic games. These are only math people actually, and from economics, and they're looking or from controls or optimization. The last point I just wanted to mention in 2 minutes is we also engage with a lot of companies, right? So with AutoWare, we have all these AutoWare runs on all mentioned in Japan, in Michigan, in Istanbul, and so on. There are over 80 companies and universities that are partners. They contribute to AutoWare, and then they all have. So our focus here is on how do we build the next generation electric and autonomous vehicle on these kind of skateboard chassis. And I won't go into the details of that. This is another lab I run, where we have a garage lab and we drive in and out and we build actual vehicle platforms over there. And y'all are all more than welcome to come there, and we'll be happy to host y'all and see that or participate in that. And then through that, we engage with a lot of professors worldwide. They all have vehicles with AutoWare running different research on all different topics, and they're all part of our network, and we sponsor a lot of their projects over here, and where we can now have a path that you can grow with complexity and higher fidelity dynamics, but you have a path to start to get into that. We build actual chassis from scratch, and this is a fully student-made drive-by-wire, brake-by-wire system, and all done in 4.5 months, like that, right? So, and then they race. Again, the whole design is open source of everything we do. The same systems are being recreated in Hungary, in Korea, in Poland, in Clemson University, and these are all students, no PhDs, and they have digital twins to work with the same chassis. And then we can race, and we go to racing competitions over here for autonomous racing. And then this is just showing all the algorithms that we work on. But that's sort of just more hands-on stuff. And you guys have such good facilities here to do hands-on racing. And then they win these competitions. I think in 23 they won the competition. In 24 they won the competition. So and then that's sort of and all these slides are available for you all to see later on. I guess we'll have Amar just send it out, and engagement worldwide with all these people who are using our platforms as we go over that, right? So I'll just wrap up over here. We don't need to see all of this. This is more on off-road research and the kind of work that we are currently doing there, right? So I'll stop here and be happy to take any questions. can, the ideal way would be that you see it emerging in the latent space. But here we pick those two because it is domain specific. It's just to come to the lowest reduced than. Yeah, just made the problem much simpler. And then we could do the counterfactual regret minimization also doesn't scale as well. So actually, even with that, we had to learn how the CFR offline. We ran the CFR also like 1 million plus times and had a small MLP actually just mimic that.
In one of the work, you showed that the opponent was also running on the Pareto optimal solution.
Yes.
And you mentioned that you just switch the policy to beat that opponent. But I'm not convinced that by just switching the policy, because another opponent is also using the optimal solution, how can you beat that? You may lose the race also, right? By frequently switching the policy.
Yeah, that's why we are really looking at if you have a certain policy along the Pareto front, counter policy that I could have, which will increase my odds of win against that policy. So it's a good point. The important point is that the opponent is not switching policies. So we can now switch along. So we are really, and that is what the conformal, the counterfactual regret minimization takes care of. Is so yeah, I know what you're saying. You're saying that they're all optimal policies, but they're not. But you have to keep switching to be able to adjust to the opponent. So they are optimal for the track, for the opponent. So now we are really looking at that interactive part. But we are holding the opponent to say, no, you can't change, only we can change. So that's just to simplify and to show that that adaptation helps. In real life, you and me both are adapting.
Yeah, both are switching.
Yeah. And then it's just much more difficult to evaluate.
About the localization by using the network, like, are you involving your networks that is something like impressive representation like knowledge, or you are like inversing the generative models like?
No, it's like more.
Like,
Yeah. We're just using normalizing flows to map the distribution of poses, sensor readings, and we are. But that's what we are using, just like you would have with nerves. And in fact, when we use the camera-based input, we use nerve for augmentation to generate interpolated images so that we have more images to work with. But we're not running nerve, we're just using nerve for the data generation. Yeah.
How do you balance between probing your opponent for information about them versus your own performance? Because some actions can lead to a lot of information, but not a huge cost.
Yeah, that's a killer question. I don't think we know that. We don't know this explore, exploit, and so we, like, for example, in designing the optimal race at the tuner car project that we had, there we just saw that some gradient free optimization algorithms like CMAES or there's evolutionary algorithms, some balance this explore exploit much better than the others. But I think that's the open research question. And there are other questions are like, can I, if you are racing and I'm racing, can I keep probing you to see and nudging you and coming close to you and interacting with you to see how you respond, where I can do system identification of your behavior, your model, to say 80% accuracy, but I only want to reveal at the most 60% of my model to you. So how can I have this system identification? But we haven't solved that. But those are the questions of, just doing figuring out this, when to explore, when to exploit. And also, like, as you come to the limits of your handling, how do you keep exploring? So one approach that we are currently working on is how can you learn from failure? We really, like most of this, reinforcement learning has rewards and then you penalize failure. But here we want to actually learn from failure because we want to come as close to this limit and keep pushing it. But we can do that in sim, but in real, we don't want to do that. So it's open. Yeah, that is actually, I think, a source of a lot of questions, research problems.
Aware about autonomous driving or just the driving management or?
The Autoware is basically the software that will run in your car. So I skipped over a lot of that, but Autoware runs on the buses, on the robo taxis, on our go-karts, on these logistics vehicles. Autoware is a full software perception, planning, control, connects to all the sensors, does the planning, does the control, and connects to your drive-by-wire system. And it is basically a portable to different vehicles. It works on like all these Prius, Lexus, all of these cars, but it also we get it to run on all of our vehicles. To get started with Autoware in less than an hour, you can have Autoware running in simulation and then running it on a vehicle. And that's part of my role in the Autoware Foundation is to help with the R&D and to help a lot of universities get started with that. So if you have questions about that, and you want to use it, yeah, we're not selling anything. I'm not a sales guy. So, but it's available for free, but it requires some expertise, some familiarity as you go about it. But the point is that it's not going to give you like a Waymo like high performance, system that is fully tuned to say San Francisco, but it'll give you a starting system that you can go and park your car in a spot, right? It won't help in and around, but all of that is there, the mapping software, and being able to do that. So we did a demo in Carnegie Mellon as part of our project, that in 1 hour, we can just get an autonomous vehicle here and make it drive around the campus just in 1 hour. We can just, but it's not like it's going to avoid all problems, right? So it's just a starter. So you can think of it as a rapid prototyping for autonomous. Yeah, it's just on Autoware.org or Autoware on GitHub.
So, thanks everyone, and please help me to thank Dr. Mangharam for his presentation. Once month, Forever Mountain, we have a Statler College.
Oh, thank you. I always love to teach. Yeah.
If you want to stay 1 minute for like a group picture, then voluntarily, don't feel forced to do.
Thank you.
Excellent. For the presentation,